Good morning. Well, it's another semester, another seminar series we start this time. We have few announcements in the back, so if you are coming in, please pick up one of the 4 pages you have there, and if you already are on your seat, we will make sure that you have a copy. One of them is the schedule for this semester for the seminar series. The other one is about the REEU, our research for the undergraduate for this summer. The deadline is coming up on the 29th. We would appreciate that you encourage, at least if each faculty encourage a couple of students to apply for, then we can have our quota that we are entitled to as part of this project. So we don't want to have students who are outside PVMU that will be attending this one while we have this opportunity. It's a great opportunity. Students will have like $2,500 free housing, free, we'll pay for their meals. Also, I think I'm going to work with Dr. Adu, maybe those who wants to have credit because in Texas A&M they get 3 credits. So maybe those who we can give them special topics or something that they can get credit for. So it's a great program, and more importantly, they will learn how to handle or reuse water. The other component is another opportunity also for our graduate and undergraduate for graduate students to apply for this fellowship that we are working on a joint project with Texas, with UT Austin. It's a fellowship, $35,000 students to apply for that and support them. So these are few of the things that I'll please pick up those brochures. Importantly, encourage students and support them to apply for that. So with that, I think today's topic is going to be given by Dr. Rajendra Sishodia. I hope I said your name correctly. Yeah. So he's a postdoctoral fellow who joined us recently. And Dr. Ram Ray, he's going to introduce him. Dr. Ray.
Thank you, Dr. Fresh. Good morning, everybody. First, I would like to wish you Happy New Year if I missed some of you, which are belated, but it still works. So today I'm happy to introduce Dr. Rajendra Sisodia. He joined us in November 15th from University of Florida, where he was doing his postdoctoral research from after 2015. He completed his PhD in 2015 from University of Florida in agriculture and biological engineering. He is a native of Nepal, like my country. And he completed his bachelor in engineering agriculture from India, Rajasthan Agriculture University. And he did a master in agriculture and biosystem engineering from South Dakota State University. But before he started his PhD and master, he had multiple years of experience in teaching. He taught 5 years in Tribhuvan University, Nepal. And then he also worked about 2 years as an agriculture engineer from the International Wheat Innovation Center. That's also in Nepal. And then he worked at National Agriculture Research Center, which is one of the single largest agriculture research institution in my country, where he worked 2 years. If you remember, a couple of weeks ago, we have a Fulbright fellow from Nepal, who is also working the same institution. So without further delay, I would like to request Dr. Sisodia to please make your presentation. Thank you.
All right. Thank you, Dr. Ray. Good morning. I will just turn on this mic as well, just in case. So today I'm going to talk about. I think I will. This one is a lot more noise. Just turn it off. I'll stay here probably. So today I'm going to talk about the work that I have done at University of Florida during my PhD and also as a postdoc. So I would like to acknowledge my supervisor, and colleagues and my friends. Um, so these pictures here, it shows if you can recognize me, that's me. I used to have a mustache and I used to have a little more hair, but now I think my PhD research has a negative correlation with my density of hair, so I'm losing a lot of them. And I was doing some flow measurements in that field. And this one here is one of the open wells which they use for irrigation in India. Typically, they use two different kinds of wells. One is the open well, which is shown here, and the other one is the drilled well that we have that we usually have here as well. So, this one is the picture from Florida, which has so this is a drainage ditch. In Florida, most of the southern Florida, it used to be flooded historically, and later on, when people started to come in, they drain a lot of land to cultivate the fields. So these are those ditches which are used to drain the fields to make them suitable for agriculture. And this is the picture here, which is in India. It shows a check dam, which is used to store the rainwater and increase the groundwater recharge. So let's move on. So before going on to our focus areas, which is in this case is India and United States. So let's have a look at how does these countries compare to other nations in terms of water resources and the use. So this slide here shows total renewable water resources per capita. What it means is that this is the water which is renewably available every year. So this is the water which these countries, on an average, receive from the rainfall. The rain falls and it goes into the streams. It recharges the aquifer. So all of that water goes into that is accounted in these water resources. That is called renewable water resources. That is on an average available annually. So this shows here that United States is not a water scarce. It does not fall into a water scarce nation. But many of the other countries like India and Middle East, UAE, Saudi Arabia here, and a lot of the North African countries, China here, and some European countries, they are water scarce. The reason for particularly these areas here, to be water scarce is natural because they are semi-arid areas, arid areas. They receive a lot lower rain than we receive here. So when they receive a lot lower rain, they also have lower stream flow. They have lower groundwater recharge. So annually they have a less amount of rain, or meaning they have annually less renewable resources every year. But that is not the case with India and China. The reason that it is lower per capita, because this is per capita, the reason it is lower for China and India is the population, because they have such a huge population. Because of that, the per capita, the number is like 1/8. But if you only look at the number for overall total renewable resources, India has around 2/3 of the resources as compared to United States. But that 2/3 number goes to 1/8 because of the population. Similarly, the case with China. So one of the ways to look into how does countries use water resources is to look at the water footprint. So that is one of the popular terms which has been used very recently. Frequently, it's been used a lot. So in this case, what it shows is that is the amount of water that is used per capita or in a nation on average to produce the goods and services that they need. So in this case here, what we see is the United States it uses a lot of water, so that means it's a high water footprint per capita. But other countries, like because they have less available water, and it also depends on the society and also the way that we live. And popularly recently, this here shows that how much water put the things into the context to understand for people to understand how much water is needed to produce the things. They have used this thing to, oh, you are using a 1 cup of coffee. How much water it takes? You are eating 1 pound of beef. How much water it takes to produce it? So that is one of the popular things to look into the water uses for different produce and products. So if you only look at the total number of how much water is used annually for different countries, India leads in that way. So this number here shows that India is the largest user of water resources on an annual basis, which is followed by China and then United States. So although the renewable resources are not that much in India, but still they use a lot more water. So what that means is that on an annual basis, they are going to mine the water. This similar to the mining the minerals and every other resource. So they are going to deplete the resources, which is basically the groundwater. Uh, but uh, but again, the thing is not as simple as that. The number, I mean, because the uses are different for different purposes. So here, this big fraction of this water is used for agriculture in India, and in the United States, more fraction of water is used for industrial purposes. So the normal trend is that for in the developing countries, more water is used for agriculture, and in developed countries like in the United States and Canada, United Kingdom, more water is used for industrial purposes. Um, and again, there are there are differences in climate between the countries. There are also differences within the countries. I mean, so let's say within the United States, we don't have similar kind of climate everywhere. It changes. Even in Texas, it changes if you go from north to south. So because of that, also we need to account for that. A single number doesn't tell the whole story. And again, there is a virtual water trade, which is so when whatever goods and things we produce, we export it outside. So that is in a way we are exporting the water, or we are importing the water because we are using water to produce the things, and that water is being imported. So that is a virtual transport of water. So there are multiple things to consider. So there are it's not a single number doesn't tell the whole story. So this is a good example of the regional differences in within a country. How can it affect the water resources? So if you look at it here, this picture here, this figure here shows the groundwater depletion globally. So this one is for the United States. In the United States, mostly the depletion is concentrated in the Central Valley, California, and also Midwest. This region is Ogallala Aquifer region, as you might be aware that because in many of the parts in Ogallala Aquifer region, we don't receive a lot of rain. So ultimately, if we are growing a lot of crops, then we are going to use groundwater, and then that's going to deplete the groundwater resources. A similar thing is in India. In India, groundwater resources are depleting, but it's not everywhere. Everywhere it's not depleting. This is the depletion is mostly focused into northwest India and parts of South India. So now that we have a little bit of idea about how does India compares against other countries, how does the United States compares against other countries, so let's move into the study to India. So the studies have shown in India that groundwater levels are declining, but are these declines statistically significant, or are these decline long-term declines? Because many of the studies that they looked into GRACE data and all of that, which was for a certain time period for 5 years, 7 years, because GRACE didn't started way back like in 1970s or 80s or even 90s. So it's not clear whether this decline is long-term, is significant, and what are the reasons for the decline? Is it natural? I mean, the rainfall is decreasing, or is it because of the anthropogenic? Is it because of the people? I mean, they are using more water, or is it other reason and other policy or something? And also, in the future, is the demand going to change? Because historically, the water demand in India has increased a lot. So it's going to continue for same way for at least some time. So that demand is going to change. And also, we know that climate is changing. So in the future, there will be changes in precipitation. And many of the places, they are already experiencing the changes in the climate, and changes in precipitation and temperature. So with all of these things, with all of these questions, we formulated three objectives. One was to look into the trends, long-term groundwater trends, to see if there is any trend, if there is statistically significant, and what are the causative factors. And the second one was the second part was focus more on a smaller watershed area to look into the effects of climate change and also the changes in water demand, future demand. If in the future, if there is going to be more irrigation, how is going to impact the hydrologic, the surface flow and groundwater storage. And the third one is to evaluate different management strategies, what different management strategies can be used in the future to increase the water sustainability. So let's move into the first objective. So like I said earlier, these are sorry. So these are a couple of open wells which are in the watershed study watershed, which was picked for this work. So these wells typically they are 3 to 4 meter or 4 to 5 meter wide, and they are 10 to 15 meter deep. But depending on the places, they can be as wide as 8 to 10 meters. And in North India, in some of the places where the water table is deep, they can go up to like 30, 40 meters deep. And this is what they used. It's a traditional way of irrigation, but nowadays they are being replaced with more sophisticated drilled wells, which is the tube well. They call tube well. So this was the study area for the groundwater level 10 analysis. This is a 3-district region. It also encompasses the 4th largest city in India, which is Hyderabad. It's here in the middle. So that was the area picked up for the groundwater level 10 analysis, and there were 3 time periods for which the groundwater levels were analyzed. So these numbers here, 22, 36, 25, these percent here shows the number of wells which have shown a decline in the groundwater levels. So it's not as big as is a common conception, because common belief is that all the wells are declining. They have a declining trend. Everything is so that is a common conception. But statistically, only 22 to 36% of wells are declining. And in order to find whether these declines are related with the rainfall or not, and then what I did was did a rainfall regress time series analysis, and then basically this groundwater level time series was regressed with rainfall, and then the trend tests were performed on the residuals. With that, we tried to remove the effect of the rainfall. So after removing the effect of rainfall, 20% to 26% of the wells, they still showed a decline. So these wells, basically what that means is that these many wells, they don't have any effect of rainfall. There is another factor which is causing the decline in these wells. So in order to find out what is the reason for those declines, so this picture here in the top, it shows on the left, it is the groundwater average groundwater level time series for all the wells. And this one is for only declining wells. So this is the result from a change point analysis. Change point analysis, what it does is that if there is any change, a sudden change in the groundwater levels, then it will detect it. So what it shows here is that on average, there is like they are going up and down, but there doesn't seem to be like a trend. But if you only look at the wells which are declining, you see that during this time here, which is this, after this time, on average, the groundwater level goes up, but for the declining wells, it doesn't go up, it goes down. So what happened at that time was that the government implemented a policy which was to provide the free electricity to farmers. So in 2004, that policy was introduced. So they started to provide 8 hours of free electricity to farmers. And because of that, what happened was that farmers, they started to drill new wells meaning more irrigation meaning more withdrawals, so that caused more declines. So in particularly in those areas where these wells were. So this plot here also confirms this effect of energy subsidy. It shows the area irrigated by the groundwater. So what we see here is before 2004, there is increasing and decreasing trend. I mean, in some of the years, when the rainfall is lower, the area irrigated by groundwater goes, it becomes lower because the water is not available. The aquifer in this area is a low storage aquifer. It doesn't store a lot of water like many other alluvial aquifer in North India they store. So this has to be filled like every year or every 2 years. So 1 year during the wet season it gets filled, and then during the dry season when you take out a lot of water, it empties kind of. And you'll have to, if it doesn't get refilled during the next season, during the next wet season, the wells are going to be dry. And the wells, if they are going to become dry, then there won't be water for irrigation. So naturally, it's going to cause a decline in irrigated area. But that didn't happen after 2004. After 2004, it kept on increasing. So that also tells that after 2004, the energy subsidy it has caused caused an increase in irrigated area, and that increase was responsible for the declines in groundwater levels. So let's move on to the second objective, which was to looking into the effects of climate change and increase in irrigation demand. So for that, we picked a smaller watershed, and this was one of the wells they have been drilling in the watershed. When I went there for data collection, they are drilling this well for drinking water, and this is a picture of a plot in the watershed, and this is the water which is coming from the well, and they irrigate it by using flood method of irrigation. There are only a few people who use the drip method or the sprinkler method, because drip always costs a lot of money. So they don't have if they don't get the subsidy for government, they don't usually use it. This is the watershed study watershed in which was picked up for the hydrologic modeling. It's a smaller area, 300-hectare area in the same bigger area where we looked into the trends, groundwater level trends. And this watershed was instrumented to collect groundwater levels, surface water flows, and all the data which is needed for hydrologic model calibration, validation, and scenario analysis. We also collected some land use data. And the land use in this watershed, because it's a rural watershed, so it's predominantly cotton watershed. They grow a lot of cotton in this area, which is most of it is rain fed. And if they have irrigation, then they also grow vegetables and rice. What was surprising in this case is that for the pump flow analysis, we also did some the flow analysis from the wells, and it shows a large variability in the flows from individual wells. Even the watershed is not a big watershed; it's a small watershed, like 300 hectares. It's not a big area, but even in that area, the flow from each of the wells, it was so different that there was like more than 300% of a difference in the flows, irrigation flows from the wells. So what it tells is that if you don't do the measurement, if you take one number, then it's going to be there will be large errors in the other water balance component, because irrigation is a significant component of the total water balance. So if you have a lot of error in estimating that component, then it's going to be transferred into the error into other components. For the modeling, use Mike 11 model. It is a distributed process-based model, physically based model. And in this one, we can discretize the horizontal model domain into different grids, depending on the requirement, whatever size we need, and whatever is our purpose, and how much data we have. And it's an integrated surface water and groundwater model. It does both the river flows and also the groundwater. If you're familiar with the models, it has the groundwater component in this model is similar to ModFlow. ModFlow is a model which is developed by USGS, and that's the model which is used for a lot of groundwater calculation or scenario analysis and groundwater resources estimation. So that is, and it also has a river flow component which you can use to simulate the dams and other water regulating structures. So for the model, for this calibration and validation, we have used, like I said earlier, we used the surface water, groundwater levels data, and it can simulate the multiple aquifer multi-layer system. So for the climate change and for the land use change analysis, basically we developed three scenarios. One is baseline. Baseline is the historical condition where we use the historical data, we use the existing conditions, and then the other one is climate change only. And in this second scenario, in climate change only, we are only considering the changes in climate. So we are only looking for changes in precipitation and temperature. So we're going to see how much the changes in temperature and precipitation, how they are going to change the hydrology, how they are going to change the flows. And the third scenario, what we are going to look into is that how the changes in temperature and precipitation, but also the changes in irrigation, because historically there has been an increase in water withdrawals in irrigation. So how that changes, and we are assuming that that will continue in the future as well. So how that increase, if that incorporated into the climate change as well, how that's in combination of climate change, how that is going to affect the hydrology and surface water flows. And these are the five global climate models that have been used to generate the climate change scenarios. The names are pretty complex, but yeah, just there to so what we did was that we used the GCM projection from these ones, and then delta change method was used to generate the future time series for the watershed. So this one here is it's a big table, but I just want to focus on the last column here in the table. So what it shows here is that how the climate change is going to affect the water balance in the watershed. So this is the baseline here. These are all the five climate change scenarios, and this shows the difference between the baseline and the average of the future climate change scenarios. So what it shows here is that the rainfall is going to. It was pretty surprising. I mean, all the five models they predicted increase in rainfall in the future. So on an average, the rainfall was increased. I mean, those models have showed an increase in 20% increase in rainfall. Um, and that increase was basically most of that increase was lost into stream flow. A big portion of that was gone into stream flow. I mean, it did help increase the recharge, but it also increased the base flow. So most of that was lost from the watershed as in stream flow. And this increase in ET is mostly a result of increase in moisture because there is more rainfall, so more moisture will be available in the infed areas. So that increased the ET and also um, effect of temperature because in the future temperature is going to increase. So with increase in temperature, there is going to be increase in ET. So this table here again, this is the third scenario which we have where we are considering climate change and also the change in irrigated area. So the rainfall increase in rainfall is the same, but that increase in rainfall is now equally distributed between ET and recharge, ET and stream flow. So what happened here is that because of the increased irrigation, there is an increase in pumping, 50 millimeter increase in pumping, and all of that pumping came from where? It came from the reduction in stream flows. So earlier, if you remember the earlier slide here, the increase in stream flow was 122. But when we increased the pumping, what happened was that that stream flow increase in stream flow reduced to 83 because we increased the pumping. So all of that pumping is going to come at the cost of reduced stream flows because water is only how much you get from the rain. Is going to if you get it from one place, it's going to be reduced on another place. So like I was mentioning earlier, well drying is very during the dry years it happens, but during if there is multiple drought years, then it happens more frequently. So this plot here shows how the well drying is going to change in the future. So this top here which shows the climate change with irrigation expansion. The bottom one is the only climate change. So this is the second scenario, only considering the climate change. And this is the third scenario where we are considering both climate change as well as the irrigation expansion. So what I'm trying to say from this slide here is that this climate change is going to help increase the groundwater recharge. So this is the bottom slide here. It's going to reduce the well drying. The well drying is going to be reduced due to climate change because there is increase in rainfall. So that increase in rainfall is going to increase the recharge, and basically that will help in reducing the groundwater storage, or it will reduce the well drying. But if it is when it is combined with the increase in irrigated area, what will happen is that it will result into increased well drying. So in the future, although climate change will help increasing the recharge and the storage, but the expansion in irrigation that will ultimately outweigh the effect of the climate change, and then it will result into more well drying. This one shows the effect of effect of climate change on peak flows. So if we see at this point here, this is a flow event with 1% probability, meaning that is a 100-year flow event. This is going to happen in the baseline climate scenario, which is the yellow line here, shows that this event is a 100-year flow event. But what will happen if the rainfall is going to increase, that flow, which is associated with the 100-year event here, that is going to be associated now with 20% probability, which is the meaning it's going to happen every 5 years. So a 100-year event, which is a flow event which happens every 100 years, now is going to happen every 5 years. Meaning the flooding is going to be more frequent and it's going to be on higher magnitude because 100-year flow event now is even higher in the climate change scenario. Earlier it was lower. This is the flow here on the y-axis. So 100-year event will be more in magnitude. So it will increase the flooding risk and flooding damages. So the third objective, we looked into different management options. So the first option, because the energy subsidy is the main causative factor behind these declines in groundwater levels, as we have seen. So the first scenario was to reduce the energy subsidy. What will happen if we reduce the subsidy by 50%? And if we convert the flood irrigated area into drip irrigated area, how much water use it will reduce? And the third one was to look into the water storage. So like I said, this one here is the rainwater harvesting or water harvesting structures. These are used to increase the recharge. In many of the other areas in the region, they also use it for irrigation. But in this particular watershed, they only use it for groundwater recharge. So what it will do is that it will increase the recharge, and then during the wet season, the water table will go up, and then when we have more storage, when the water gets filled during the wet season, then you can use it during the dry season when when the rain, we don't have much of rain during the dry season. So here it's for dry year, normal year, wet year, and then different climate scenarios. So what it basically is showing is that if you use a single method of single management option, this is not going to help much because this is the baseline scenario here. This is the well drying under the baseline condition. And even when we adopt other methods, if you only do one method, I mean, during the dry years, it's not going to help much. But during the wet years, it might help. But a single method is not going to help because this is no intervention. If you don't do anything, the well drying is going to increase. If you only do water storage, the well drying will reduce a little bit, but it will still be higher than baseline. So what it means is that a single method of increasing the water storage or water resources is not going to work. It needs to be complemented by other methods. I mean, supply and demand, they need to go hand in hand. You also increase the supply, you also try to reduce the demand by using the methods which also uses less water, like drip irrigation. So you have to combine different methods to reduce the well drying in the future. So with those analysis, what are the large scale implication? How does it translates into like a bigger picture? So what I'm trying to show here is that from the modeling, we have known that if we increase the groundwater withdrawals, is going to increase the declines. So there's going to be groundwater decline. It will increase the well drying, and what it will do is that well drying, when the well is dry, you don't have much water for irrigation, so that will result into crop losses, and around 70 to 90% the modeling showed that this much of area will be affected in the watershed with the well drying. And also the groundwater decline, what it will do is that so when the water declines, you have to lift the water for the higher head. I mean, the head of the lift head is going to be higher. You will need more energy to lift the same amount of water. So that will also increase the energy requirement. And on the other hand, when we are increasing the groundwater withdrawal and we need more energy pumping the same volume of water, what will happen is that it will also reduce the stream flows because we are pumping more water from the ground. So what will happen ultimately is that the water is going to recharge some of the aquifers and moisture. So it will reduce the stream flows. So there will be reduction in stream flows. What that will do is that it will reduce the energy generation power. They have a hydroelectric dam there. So it's a kind of like a double whammy. I mean, you will need more energy, but you won't have enough energy. You won't be able to generate more energy because you are losing your surface water resources. So that is a complicated cycle. So the proposed management option, if we reduce the subsidy, what it will do is that it will reduce the amount of money that you are spending. So that money can be used to install the drip irrigation, and then it can also be used to install the water storage structure, which are going to increase the groundwater recharge. So what it will do is that it will reduce the energy consumption, because drip and water storage is going to increase the groundwater levels, so that will reduce the energy consumption, and it will also reduce the carbon footprint. And also because there will be less well dryings, which also is going to increase the household income from agriculture. So to summarize, the takeaway is that there are declines in groundwater levels, but it's not as widespread as is a common belief. There is 22 to 36% of the wells are showing a decline, but it's not like all the wells are showing a decline. And in terms of climate change and future changes in water demand, what will happen is that climate change will help reducing the stress on the water resources, but it will also increase the frequency of the floods. So but when it is combined, when climate change is combined with future increase in withdrawals, which is likely to happen, so then it will be there will be more increase in floods, and also there will be more increase in well drying. So that scenario is the worst scenario, where you also increase the water withdrawals, and then climate change is also going to worsen the drought and the floods. I mean. So now, so this one is moving on to the other section, which is Florida. In Florida, there is so this slide here shows that this is one of the ranches in Florida, which is this is a drainage ditch, which they use to drain the field. During the wet season, they use these ditches to drain the field, so that they can grow grass or whatever other crops they want to grow, because during the wet season, the water table can come onto the surface. In South Florida, the hydrology is shallow water table, so that's why you have to manage the shallow water table. And during the dry season, again, these same ditches can be used to irrigate the areas. So what they do is that they call it a seepage method of irrigation. So when they flood the ditch to a certain level, the water is going to go from below and then going to go into the field. From the ditch, water goes into the field from the bottom. So it will provide the water to the root zone from the bottom. So that is a method, one of the methods that they practice in Florida. And this picture here on the right, it shows one of the structure where they install wooden boards on a culvert riser board that they call a culvert riser board structures. And what it does is that basically it will stop the water from going downstream. That will store the water into the ditch, and then stack the water into the ditch all the way to the end. So why they are doing it? Because I'll show you in this slide here. So this is Florida here, and this is the existing. These are the existing canals. This is Lake Okeechobee in the middle, and these are the canals which goes from Lake Okeechobee to the south. And these areas, they are all agricultural areas. They are very fertile lands, and then they produce a lot of sugar cane. The areas in the north here, all the water from the north, it gets into Lake Okeechobee. It's also a reservoir, so it stores water, and it provides water during the dry season to irrigate those areas downstream. But and also when the lake levels get high, it will release the water to the west to Caloosahatchee, and to the east into the St. Lucie River. But it wasn't like that before. So earlier, what it was like is that this was the Greater Everglades watershed. So what will earlier all the water will flow into the lake, and from the lake it will go downstream like a sheet flow. So it will be a wide sheet, and then water will flow in a wide sheet all the way to the Everglades National Park, which is here. But what they did later on, settlers, is that they want to cultivate, because all of this is very fertile land. With all of that water coming into it, it has a lot of sediment, which has a high fertilizer, high organic nutrient content. So they drained all of these areas for agriculture. And so now what happens is that all this water from here, it does not go into Everglades National Park. And this is at risk because it doesn't receive the water it needs for the ecosystem services that it is providing. So So what happened is that it has disrupted the natural flows. And because of that, the storage capacity of these lands is reduced, even here in the northern part as well as in southern part. So because of that, what happened was that all the water which goes here in lake, they had to release it somewhere. They cannot, in the wet season, they cannot let the water go all the way to the south. So what they do is that they release the water east and west to these rivers, and it goes into the estuaries. And these estuaries, they are saline water system. Florida is a big tourism industry. A lot of people come there to go to the estuaries and all of that. So it provides a lot of ecosystem services as well. So what it is doing, all of this fresh water, it has a lot of nutrients as well. So it goes into the estuaries and it damages the ecosystem. It kills the seagrass and also the oyster, and basically it is damaging the ecosystem, estuarine ecosystem. So it's damaging the tourism industry and all of that. So what the state did was that they started. I mean, actually, the federal government, they started a large restoration project. It's in the history, I think, globally, it's the biggest restoration project. They're spending billions of dollars to restore Everglades, and a part of that was to look into the different methods so that they can reduce the flows into the lake itself, because the water is coming from the north. So they need to create a storage north of the watershed, north of the lake, so that when less water goes into the lake, they don't have to release that much of water to the estuaries. So it will. So meaning they are trying to restore the water storage potential of the lands north of the Lake Okeechobee. And in 2006, they started a project which was FREST, Florida Ranchland Environmental Services Program, and it was at a pilot scale. There were 8 ranches which participated into this program, and the ranch which I showed earlier was Buck Island Ranch. It was a part of that project. And later on, it went on to bigger scale, and then it was implemented onto our more ranches. So this is the watershed. We are still working on it, and the manuscript is not published yet, so this is still work in progress. But like I said earlier, we are trying to restore the storage capacity of the watershed. In that, we're trying to increase the storage into the ditches by raising the spillage elevation into the ditches. So what you do is that you put a board. So there are wooden boards. The boards, if the more boards you add, is going to increase the spillage elevation. So that meaning it's going to stack more water into the ditches. And what it does is that it decreases the flows which are leaving the ranch land. So that's what the government, the state is paying them from. So they do an estimation based on a hydrologic model, and then they do the estimation. Okay, so we are going to increase the spillage level by this much, so it's going to result in that much of reduction in flows. So for that much reduction in flows, that's how much money we are going to provide the ranchers or the landowner. So the government is paying the landowners for that. They are not doing it voluntarily for free. I mean, nobody wants to flood their land, so the state is paying the money for flooding their land or to retaining the water in ranch lands. So what modeling result shows here is that increasing the spillage level, it reduces the flows from the watershed. It basically it verifies the concept, and then it shows that it is mainly happened with the increase in water storage into the ditch and also on the land surface. So what it also does is that, because when you are increasing the storage into the land, what it does is that you are reducing the wet season excessive flows, but you're also, because you're increasing the groundwater recharge, so that increases the groundwater storage, and it will be released later on. It will release later on during the dry season. So all of that reduction in flow is going to go downstream to other areas, and it will help increase the base flows during the dry season, which is much needed for irrigation and all of that purposes. So basically, this slide here, I won't go into much of the detail, but what it is showing here is that it will also help reducing the peak flows into the regional rivers and canals. So this peak here, it is related with one of the tropical storm event, and during that event there was a large outflow event. But these increase in spillage level, it can help reducing the peak flows from those events. So it's going to help reducing the peak flows into the lake as well. This one also, I won't go in much detail. This is we also did a comparison because the state is using a model to pay to the landowners, and that is an empirical model, which they are using to estimate the services, to estimate the reduction in flows. That's what they call. So that model is empirical model. It has some limitation because you cannot use a physically based model every time you are doing because it has complexity, it has computational time. You have to set it up, calibration, validation. It takes a lot of time, expertise, and money. So. So that's so because of that. So there were some differences between this model and the integrated hydrologic model that we used. So that model which the state is using, they need to modify it to reflect some of the subsurface flow processes which that model does not represent. So this is another side which we, uh, in this case, this is one of the another PS side which I was mentioning. So in this case, what it does, what the state pays for is that whenever they expect there are a lot more flows are going to come into the lake, what they will tell the landowner. So this is a 1,000 hectare impoundment. So they will ask the landowner to pump the water from the public canal. So this canal is going into the lake Okeechobee. So when they see that more water is coming into the lake, they will ask the landowner to pump the water to the impoundment. So that way, this is one of the ways to reduce the peak flows to the lake. And what it does is that it will reduce the peak flows and also it will do the nutrient retention because the water is passing through the impoundment, the whole area. So through the settling and all of the other processes, it is also going to it is also going to retain a lot of nutrients. So this one here, so this slide here also shows that yeah, there will be a reduction in it will retain a lot of nutrients, and then a lot less nutrients are going to go into the downstream areas. But there are also trade-offs. When you retain a lot more nutrients, it's going to increase the phosphorus and nutrient storage into the soils, and then ultimately they are going to run out of their storage capacity. They can only store so much, and also there will be ecological consequences. I mean, what we have seen in that area is that the cattail, which is like invasive species, which is I mean, the footprint of that cattail increased a lot because of that nutrient retention. So all of these trade-offs they needs to be considered. So this is my last slide here, where I'm trying to show the other projects which I've been working on. Uh, if you want to see, this is the system that they use in Florida. This is plasticulture they call. Is they lay the plastic on the ground and then they will plant the crops under the plastic. They fumigate this plastic for to treat the pesticides and all of that, and then later on they plant it. So that is called plastic culture, and then what we have been doing is trying to simulate the plastic culture and see to find different ways to increase the irrigation efficiency and also to reduce how can we reduce the inputs. And also, like I mentioned earlier, the nutrient retention in ag stormwater areas, because by regulation also many of the ag areas they do require that they have to have an impoundment. You need to have an impoundment before, because they need the impoundment at the end of the farm, because they need to store the first flush of the rain from the season, because there are a lot of nutrients in that first flush. So that's why. So how can we increase the efficiency of those stormwater impoundment? That was another project I was working on. Yeah, so that's all I have.
Thank you.
If there are any questions.
Let me start with a question. I'd like to ask you about, first of all, this is a good presentation. Very nice, well done.
Thank you.
Lots of work. I guess about the downscaling that you did from the low circulation model to the watershed scale. What kind of downscaling did you do?
Yeah, so one of my committee members in my PhD committee was Dr. Jim Jones. Probably you know him, and he is associated with one of the projects which they are working on. He's a crop modeler, so they have this website they call AgMIP, which is Agriculture Model Intercomparison Project. And what they do is that they have their own team, the climate experts, and what they do is that they will prepare the downscale scenarios for all the areas for different grid sizes for the whole world. And then if you need downscale projection, then they will provide it to you for free. So that's what I did, because he referred to me referred to that thing. And then they have a set of 5 global climate models, and then it represents a range of uncertainty also. And then and those climate models, they are also they predicted the historical weather prediction is good for the region. So they use a downscaling method which they call, I think, delta method. It's a modified delta method. And what they do in that is the global climate model prediction, they provide a change factor from historical to future time series. So they have like different time slices for the future, 2030 to 59 or 38 time slices. So based on that, you have a change factor for each of the month, and that factor is applied to the historical time series. And they also do some other more refined processing for that, but that's basically the process. I mean, it's a statistical downscaling method. It's not a dynamical downscaling.
Okay, thank you. Any other question?
The water farming programs in South Florida around Central Chile, those were predominantly beef cattle farms, because there's a lot of dairy here.
Yeah.
So I'm wondering if there's no of that increasing usage for animals on those ranches where water farming.
No, I don't think so. I mean, the cattle farm.
By the way, his information is based on the needs.
Oh, okay. Yeah, no, but what I have seen is that I think more the, yeah, I mean, they have a lot of cattle and a lot of ranches in that area. But when what happens is that if you flood a lot of, I mean, if you store a lot of water, then what's going to do is that it's going to flood a part of your ranch. So in that way, you're going to it will hamper the production. I mean, you won't be able to move your cattle to those areas. So I haven't seen how if it is affected. I don't know of, but probably if it is, I would think about it. Then I would think that it will. If you are going to store more water, then naturally you will have less space for the cattle. So it will have probably a positive effect. But I haven't looked into has it actually been changed in that way or not. But that's just my prediction.
You're right, it was very having all those days yeah, especially the phosphorus level that they are dumping into the lake. That was one of the biggest issues. So almost started the industry there around the Chile.
Yeah, it was mostly in North Florida, actually, the northern part of Florida. That's what I've seen. There are more beef cattle in that area, in the southern side of Florida.
I think I have one more question. Question is about the increase of the rainfall based on the prediction, based on the climate change scenarios. There is one thing that you talked about it, but I think is going to impact the composition of the recharge and the stream flow, which is the frequency distribution of your rainfall event. So as you mentioned about that 100 year event, it will be
5-year event. It will be
25 years event. So the frequency of the extreme event
is going to increase.
Higher, which means less time for the water to infiltrate, which basically less water for groundwater to recharge.
Yeah.
I don't know if you had a chance to take a look at the impact of that frequency distribution on the composition of the distribution of the water, the groundwater discharge versus stream flow versus.
Yeah, I haven't specifically looked into that because if I had to predict, then what I will think is because that aquifer in that area is a low storage aquifer. It's not like an alluvial aquifer. So if there is going to be like an increase in peak flow, it won't be able to store that much of water in one time because it is naturally limited by its capacity. And also, if the runoff is going to be quick, then there won't be enough time for infiltration, like you said, and there will be less recharge, and it is going to increase the flooding risk ultimately. That's what it would be.
Yes.
Yeah. No, and only for that area, for that particular area, because what they provide the projection is for that particular watershed. So that applies to certain size of the grid cell that they are doing. So it might be like half degree by half degree grid. But overall, I think for India also, most of the areas they are going to receive more rain because of the climate change. That's what I think. But it's not like it's not equal for all the areas in India as well. Some of the areas they are going to receive more. Some of the areas they are going to receive less. That's what the global climate model prediction is. But then again, they are also uncertain. I mean, there will also be changes in the extreme events like the low rainfall events or high rainfall events. So it's all uncertain, but it's still overall, I think for India there are predictions for higher rainfall in the future.
Any other questions? Anybody has an announcement about the new person who joined us? Well, thank you very much and have a good day.
Thank you.